Welcome to the Day of Datomic training videos. In this first video, Stu Holloway will introduce Datomic and provide an overview of Datomic's architecture.
We're going to get started. Good morning. My name is Stuart Holloway. And boy, it's really cool if can you guys feel that coming off the back wall, the echo? It's like, hello. Oh, that's an actual person on the back wall. That's totally separate. My name is Stuart Holloway from Cognitect. I'm here with my associate, Marshall Thompson, who's going to be making sure that all the labs and so forth work. And I'm super excited to be here kicking off ClosureConf 2016 with a day of Datomic. Got a good group here and looking forward to a fun day. Just a couple of logistical notes. At some point, we will break for lunch. Technically, did we list that this was going to go until 5? Is that more or less? That seems like a good business day. All right, so the truth is we're going to go to about 10 p.m. tonight. Bonus material. No, we'll stop more or less around 5, or at least move somewhere more comfortable. Given that halfway between 9 and 5 is, let's say 12:30. Let's break at 12:30 for lunch. So we'll break at 12:30 and take an hour for lunch. I will remain in the room, so if you have questions and want to talk about things over lunch, instead of in front of everybody else, if you have embarrassing questions or whatever, you can approach me at lunch or at one of the breaks. So we're going to get started, and the way we're going to roll today is we're going to start. This session is going to be just an overview of Datomic, and then we're going to have 5 other sessions. We're going to talk about the information model of Datomic. So this is really the most important thing about a database. If the information model doesn't let you find out answers to questions you would like to ask about your database, then its operational characteristics are not going to help you very much. And the mechanics of using it are not going to help. So that's why that leads. Then we're going to talk about the model of how data gets into Datomic. And to just go ahead and spill the beans right now, it's the most ACID transactions you'll ever see. So this is a strong, old-school ACID transactional database. Then we're going to look at the query model. The query model, I'm going to use the word query here in the broadest sense. We're actually going to look at Datalog, which is the query engine that Datomic has. But we'll also look at pull. So Datomic has a model for making hierarchical selections from data. So you can do logic-based query to locate things, but you can also say, I already know what I want. I'm interested in this particular thing, and I would just like to be able to pull a hierarchical selection of information about this entity, starting from somewhere and navigation. So pull is more of a navigational model, and Datalog query is more of a logic-based model. And then we'll also look briefly at raw indexes. So as a sort of toolkit, Datomic also provides direct access to its indexes, so you could build your own sort of tool on top of that if you were integrating it with a big data analysis system and other systems, and you can go and get the indexes directly. And then we're going to talk about Datomic's time model, and this is arguably the most distinctive feature of Datomic. Datomic is an accumulate-only system, so it doesn't forget things that it knew in the past, which seems like a desirable characteristic for a database to have. And once you get used to working with a database that works this way, you wonder why databases haven't always worked this way. And it's a good question, and we'll explore it a little bit. And then we'll finish by talking about the operational model for Datomic, which got a lot more interesting as of yesterday's release. So we have released a new operational option for Datomic, which we're going to actually be kind of leading with in the class today. And using that, in addition to being an important new operational model, it's probably the best model for getting started in a classroom environment. So we will actually be operating in the class today using Datomic clients. So pretty exciting there. So what is Datomic? It is a database that is designed for the ground up for functional programming in the cloud. And there are some characteristics that come out of this. I like the word agile, even though the word agile has been perhaps drained of meaning by becoming so popular. What I'm talking about here is the ability to move quickly in a direction that I want to go. And if you've built a system, how many people here have built a system and had to live with it for more than 5 years and continue to make changes to it, right? I can tell you the day in which your past choices become the elephant in the room and dominate what you're able to do going forward. It's day 2. Right? And so if you've built a system and you've lived with it for 5 years, you know what that's like. And so, and this is, I'm leading with it here on the slide, but in some ways it's the most subtle point because you have to spend lots of days with something to really appreciate that. I have now spent 9 years with Clojure and all of Datomic's years with Datomic, since we started developing it. And so really knowing that if I keep my wits about me, this is a database that is not going to paint me into corners. Right? I'm not going to just, so we're trying to shrink the elephant in the room factor. Now, to be honest, the elephant in the room factor is still huge because doing this is hard. Making things, simple is not easy, even though some other conference speakers have given talks like simple made easy. It may be easy for one person, but it's not easy for most of us. And so that's still there, but Datomic gives you a fighting chance to build a system that you're going to be able to modify easily as you move forward. Datomic helps you build systems that are robust, right? Systems that do not fail in mysterious ways and that are easy to understand. And I'll say right now that I'm not going to make any claims about systems never failing. We all know how this works, right? We all know. I saw a quote the other day. Let's approach this retro knowing that we're going to be as stupid tomorrow as we were today. Right? We're going to make mistakes. We're all going to make mistakes. But how are our systems going to be robust in the face of those mistakes? And a dominant characteristic here is that accumulate-only nature. Right? When you have a database that only accumulates, you can say, I would like to wind back in time to that point 4 days ago where we were making that horrible mistake. And I would like to look at the database right before we made the horrible mistake. And I would like to look at the database right after we made the horrible mistake and try to reason about it. Well, how do you do that in a system that's not accumulate only? It's a big mess, right? I mean, you basically say, okay, let's figure out where the logs are, and let's try to reconstruct from the logs, the operational logs, what happened in the system while things were going wrong. But the actual thing that was there when it was falling apart and excrement was hitting the oscillator, it's gone. Right? That thing is gone, and you have to reconstruct it in your mind, which is extremely difficult. I want to feel powerful, and this has definitely been an up and down journey for me in 25 years as a software developer. I want to sit down. Feeling powerful for me is having the difficulty of the work scaled to the difficulty of the problem, but not more difficult. Right? So if you sit down to do something hard, it's going to be hard. When I sit down to do something easy and it's hard, I feel weak. I don't feel powerful at all. If I sit down to do something, well, this should be totally straightforward, and then it takes 6 days, and this Maven dependency over here causes that thing to break, and this thing fails without giving an error that tells why it failed, but the library that was consuming it just eats that, and then it passes up the chain, and the symptom happens over here. Those things make me feel not at all powerful. And so I would like the difficulty of my tasks to be related to the tasks themselves and not the tools that I use to try to solve problems. I want a database that can remember the past. Again, this seems blindingly obvious in retrospect, but there were a series of choices that were made in the 60s and 70s about how to model information and records that we're only sort of just now getting over. And I want to be ready for the cloud. And this was part of Datomic's design from the first minute. And if you look at the way the Datomic pieces fit together, when we talk about the operations of Datomic, you'll see that it's made of small components that are designed to be deployed separately, that are designed to fail and be replaced easily. Right? These are all important aspects of operating in the cloud. We can do more. It's certainly an ongoing thing in our development of Datomic to better and better target running in the cloud. But from day one, it's designed for that. And this is a huge deal. In the course of building Datomic, I've been forced to depend on a lot of traditional data center software that has been moved to the cloud. So I don't know how common this expression is, lift and shift, where you take existing data center software and you just start running it in the cloud. And the thing is, that existing software that was written or thought, or the ideas behind its writing are decades old, tends to assume that it owns a box. And it tends to assume that that box is important. And so I've ended up doing things like writing a script that says, okay, there's this precious configuration file for some tool that we use. Well, we've now lifted and shifted. So where does that precious configuration file live? It's on a box in the cloud somewhere, a deliberately ephemeral box. Well, what happens when that deliberately ephemeral box goes away, which we should plan for and expect? Well, the precious configuration file goes away. And the data center software doesn't know any better. So then you write a tool to synchronize the precious configuration file once an hour somewhere else so that you don't. But of course, this involves reverse engineering what exactly it is that's precious about the configuration file, because the thing says, well, the security credentials and this and that and the other go in this file, but then when you actually write that tool, you discover that it depends on this other file over here. That's not mentioned in the documentation. So there's so many ways that data center software can trip you up. And I've had to live that because I still have to depend on, a subset of the tools that I use are still designed in that world. And it pains me every day, and Datomic is designed not to put you in that situation. So one of the things that really helps Datomic be agile is the idea of a universal schema. Right? In a certain sense, Datomic is relational. And people say relational database. But an actual relational database, a traditional SQL database, has you define 5 or 10 or 100 or 1,000 different relations that are manifest as tables. With Datomic, you never define a relation. There is a single relation. It's a universal relation. And the universal relation is of 5 tuples. So if you pictured modeling this in SQL, if you actually just wanted to implement a really impoverished Datomic-alike in SQL, then what you would do is you'd have a table that had 5 columns in it: entity, attribute, value, transaction, and operation. The entity is the identity of the thing you're talking about. The attribute is a name identifying some property of that thing. The value is that property. So Stu likes pizza, right? Entity, attribute, value. And those 3, if you just stopped there, you'd have what people call a triple store. Right? You'd have something that's stored. And that's a big reason that triple stores came into existence, was to get exactly the same kind of agility that we're talking about here. And triple stores start to look really nice if you're modeling something like an inventory database. Right? So you have an inventory database where you have thousands of parts which have tens of thousands of distinct attributes. But an individual part doesn't have 10,000 different attributes. Right? Each individual part has some small set of attributes and somebody else has a different set. And so what happens when you try to actually make relations in a traditional relational database to do this? It gets ugly pretty quick, right? Do you make a table with 10,000 columns, all of which are nullable? Right? Because any particular thing may or may not have, those things. So the universal schema helps you model data when you don't get to dictate that everything has to show up in a box of a certain shape. And a lot of our systems have that characteristic. Not all. There are certainly, domains where everything shows up in a box of a certain shape. Right? If you're processing log files, right, everything shows up in the box of a certain shape. It's like, date, timestamp, process ID, blah, blah, blah. And absolutely everything has that shape. But if you have a system where things occasionally have a different shape, then this agility is super helpful. So we're coming from a world of update-in-place systems. And you see this with databases like Datomic, but you also see this in trends in programming languages. Right? For decades now, we've done primarily imperative programming where data structures are update in place. So if you have an array, you can just reach into it and replace the 5th element with something else. And this has dominated the way computer science is taught. It's dominated the way, if you look at, say, the top 20 programming languages by any measure. Right? You can look at kind of a lagging indicator like the TIOBE index, or a leading indicator like analysis of usage on open source. You will see that the dominant languages work this way. Right? And we know what they are. Right? There's C, C++, Java, C#, but also Python, Ruby, et cetera, et cetera. Right? These languages are all update in place. And update in place makes programs difficult to reason about, because if I'm sharing something with you and either one of us might update it, now we have a coordination problem. I have to worry about what's going to happen. Am I going to update it? Are you going to update it? What happens if we're both updating it at the same time? If I want to distribute something, if I want to hand something out to people, but I'm going to hand it out with the promise that it might change later, again, you have a coordination problem. Concurrently accessing those things is hard. When you access something that's update in place, and this is important for databases, if something is update in place, when you access it, you had better get every piece of information you want eagerly. Because if you don't, what's going to happen when you come back 5 minutes later? It's going to have changed. Right? You're not going to have a sound basis for reasoning about. And of course, if you've ever heard the phrase cache expiry, you know you're dealing with update in place, tech. right? Because what would the expiry policy be of data that didn't update in place? Infinite, right? You can go forever, right? You don't have to have cache expiry on something that's not updated in place. You can say, well, look, this is what it is. It's never going to change, so we can cache it as long as we want to. And programming has been dominated by this. And interestingly, in database programming, I think has gotten a lot more interesting in the last 10 years with the NoSQL movement. But most of the NoSQLs don't really touch this, right? They continue, they are modern in other ways, but they continue, in many cases, to be updated in place. And they also continue to be very data center oriented. So if you take one of the more popular NoSQLs and you want to go run it in the cloud, right, that's its own, additional problem that may be actually the most difficult thing about it. Contrast this with building with what are called persistent data structures. So data structures that preserve their past values. And this is the way Clojure works. This is the way F# works in the Microsoft ecosystem. This is the way Haskell works. Right? There are languages out here that are doing this. And people that are using these languages are having a much easier time building robust systems because they don't have to worry about coordination. And if you go back to my notion of being powerful, right? If you have to coordinate over something unnecessarily or in a way that's unrelated to solving your problem, that's horrifically complicating, right? I'm trying to do this, but I'm worried about you reaching in and touching something and breaking me. That has nothing to do with me solving my problem, right? I don't want to be thinking about that at all. So to get an idea of what the time-aware notion of Datomic looks like, I'll show you a couple of different sort of ways you can look at data. When you're working with Datomic, you're always working when you're querying or doing a pull or accessing the index from a database value. So you have a thing that's not the connection. Right? You have a connection, maybe, depending on how you're accessing Datomic, but you also have a value, and that value is the value of the database at a particular point in time. You have that in memory. It's never going to change. But given that value, you can say, give me a new value that is as of a point in the past. So take the value right now and say as of 10 hours ago. Now you have a value that has all the recent stuff filtered out. Or you can say, give me a value that's since some point in the past. So now you're saying, you know what, I only want to see a sliver of what happened recently. So give me everything that happened in the last 10 hours, but nothing else. You can also get reports of transactions. So you can watch a running system and tap into it and get reports of transactions as they happen. And because everything is accumulate only, that transaction report has some pretty interesting things in it. It has in it the new datums, the stuff that's new that got added in the transaction. It never has any subtractions, right? Or accumulate only. So there's no datums disappearing. It has new datums, but it also has in it the old value of the database and the new value of the database. Right? So what was the value of the database before the transaction? There's one seat in the front here, at least. Maybe there are others. And the value of the database after the transaction. You can also do speculative work. So you can say, I would like to know what the database would look like if this happened, but I'm not really ready to commit to this happening yet. And that's called with. So with is an operation that takes a database value and returns a new in-memory update. So this is not a real change to the database, but it has all the semantics of the database. So you can say, if I did this, what would happen? And people have done some actually surprisingly interesting things with this, where they will build up a whole stack of transactions locally and do sophisticated transaction spanning analysis and validations to decide that they're happy, and then only bulk submit the transactions after testing it out locally. And then, of course, you can get what's called the history view, which is a timeless view. So the analogy here would be, and I'm going to come back and beat up on this analogy later, the analogy of looking at history would be moving from your source code to your Git repo and doing a Git log search where you can search both what's happening now and what was there yesterday, but not before yesterday, and then what was there before that, and so on. So that's the basic model. And then just briefly, we'll talk about the operational model. So, and this is where sort of things break from the traditional, the database is a sort of sacred thing that happens in one place that's more traditional with data center software. So if you think about a traditional data center SQL database, that database does everything about being a database, right? It implements storage, it implements transactions, it implements query. And what that means is that it's challenging, and I'm not going to say impossible, but it's challenging to make independent decisions about storage or transactionality or read or whatever, because it's already built to all happen in one place. And because, and this is a theme we'll come back to, because it was designed all to run in one place, it tends to make presumptions. I mean, try to build a system that runs all in one place and then break it apart and distribute it without having thought about that in advance. And you'll discover the challenges, and you hear like scary words like replication and things like that, start to come into play. Now, what Datomic looks like is quite different. There is and I'm going to describe these as services. I mean, they're services in the generic sense, but they're made up of groups of processes. There is a service called the transactor, and the transactor does transactions. That's what it does. It implements transactionality. It does not do query. It does not do storage. And so this provides an independent place in your system where you can manage and scale and think about transactions. The transactor service currently also does indexing. This is an example of yet another split that could be made that we haven't made today, right? But right now, that service is composed of a set of processes, usually two processes, right? And the reason that this service is two processes is that it's a single writer system. So there's one process that's trying to commit changes, and then there's another process that's ready to jump in if that process becomes sick. So usually that's going to be a two-process collection. Then there is the storage service, where things are actually placed durably. And that is a collection of processes and disks or RAM or whatever we trust to store stuff. And there are a bunch of different choices about that, and we'll come back and talk about those later. So Datomic models the durable storage separately from transactionality. Then there are what are called peers. Peers provide access to query, and peers are the same distance from storage as transactors are. Right? Transactors do not live with storage. Peers do not live with storage, but they're just as close, which is why they're called peers. Right? Everybody has equal access to the underlying storage in the system. And peers come in two flavors. There is the peer library. So the peer library is a jar file that you put in a JVM-based application that gives you in-memory access to query. So you can do query and pull and indexes and all that at memory speeds, which for certain kind of problem domains is stunning, right? Because it takes an RPC hop out of your overall architecture. On the other hand, there's also peers that are themselves servers. So a peer server is a process or a group of processes running in this role that act as servers and use HTTP as their protocol, and then clients, more traditional clients, can talk to them. So as an application developer, you're going to do one of two things. You're going to write a JVM-based process, and you're going to embed the peer jar in that process. Or you're going to write a process in an arbitrary language and use a client to connect to a peer server. The latter, which by the way was released yesterday, right? The latter is a more traditional architecture. It's easier for people to sort of walk up to. It's like, well, what is my job as an application? What's my role as regards the database? Well, your role is to be a client, right? You call over to somewhere else, and it does the work. And so that's what we're going to be doing today. Now, another characteristic of being split apart like this and of being accumulate only is that memcached becomes a transparent addition. So think about what happens when you typically add memcache to an application, right? You go and identify a hot query, right? Looking up the user's ID and password because we have something where they're logging in all the time from their cell phone and checking, whatever. That's a hot query. So you write custom code to put that in a cache, and then of course you have all those cache coherency, questions like, okay, we put that in the cache. Now how do we keep track of making that cache stay in sync with the data and so forth? With Datomic, the thing that goes in memcached is just the raw indexes of the database. And this happens transparently. So all you do is walk up to a system and operationally say, you know what, in between my peer or my client and the underlying storage, I just want to put in a memcache layer of yay size with this many machines serving it. Nothing else changes. How much code do you have to write? 0. What do you have to do in order for that to tune to get the hot stuff in the cache? Run your system. What do you have to change if your system's characteristics change and have different load? Nothing. What happens? Here's a good one. What happens if you wanted to serve a transactional load and an analytics load from the same system and they had really disjoint hot sets? Run 2 memcache clusters and configure this set of peers to use this memcache cluster and the Datomic transactor, and configure that set of peers to use that memcache cluster. What do you then have to do to tune them to actually get the right data that's hot in them? Nothing, right? And this stuff is a big deal. It's not a big deal on day one, right? If you work in an environment where you write programs and get to walk away from them and somebody else has to make them scale or operate or do the second thing they have to do a year from now, this doesn't seem like a big deal. But if you have to live with a program that evolves and serves more than one need ever, then these kinds of things become a really big deal. All right, so that's the grand overview of what Datomic is and what we're going to be talking about today. In a minute, we're going to break and get everybody set up to use the tools and run the lab. But before we do that, any questions? There has to be at least one question or we don't go forward. Yes, CJ, right? Right. I skipped that, didn't I? Yeah. Boy, I'm just so excited. I'm just skipping over stuff. So CJ asks, wait a minute, you skipped the other 2 things. So unlike a triple store where you have entity attribute value, a datum also has transaction and operation. So transaction is a reference to what's called a reified transaction. So transactions themselves are entities in the system. So that tells you how the data got here, who put it in. And importantly, it tells you when and in what order. Because that transaction itself is another entity which has associated with it a growing only number that represents the order in which things happened in the system, which is totally consistent. It also can tell you the wall clock time that data was put in the system. And then the 5th item, the op, is really just a Boolean, right? True means we're saying that this datum exists in the system, and false means we're retracting it, right? So it's assert or retract. And that's how you get the semantics of something going away without ever having any delete or update in place in the system, right? You can say, Stu likes pizza, and then 5 hours later you can say, Stu needs to lose a few pounds. Stu is going to try to tell himself he doesn't like pizza anymore. But it's not, I can say that in the database. Whether or not it's true is a separate deal. Any other questions? Yes? So you have to implement something that forgets things, right? So in an update, so the question is, how do I deal with, and is it Kirill? Yes. Kirill, nice to meet you. So how do you deal with systems that are obliged to forget? So this is yet another place where update in place systems are a catastrophe, right? Because with an update in place system, if something's gone, you have no idea why it's gone. You don't know if it was deleted because it's no longer true, or if it was deleted by accident because of a bug, or if it was deleted because of a privacy act or something that says, data has to be removed. So Datomic has a feature, which I will talk about once now and once at the end of the day, called excision. And so what excision does is it says rewrite the index, obliterating some subset of the data that's in the database. But it's an explicit act, and the act of excision is itself logged in the database. So obviously, there's a bit of a circular problem there, right? If you tell me remove, Stu says he didn't even want to be registered in your system, and the fact that you know that he likes pizza is really ticking him off. So he wants that fact removed. If I have an excision record that says, yesterday we removed the fact that Stu likes pizza, that doesn't quite accomplish the job, right? Because now we've just replaced the Stu likes pizza with we remove the fact that Stu likes pizza. So an excision record will tell you non-identifying things about what happened. So an excision will say that Kirill came into the system yesterday and ran a transaction that obliterated values for the likes attribute. It won't say what entity they were or what their values were, but somebody removed likes from the system. And that's nice because one of the problems with excision is it completely undermines the understandability arguments I made earlier. It sucks, right? It's necessary. We understand that sometimes data has to be removed. But when you can magically remove data and make it appear as if it never happened, then you're very much damaging your ability to reason about the system. So you excise data from the system, and somebody comes back, a month from now and says, hey, you lost my paycheck. Now, really, this is a bad actor who actually used a Privacy Act thing to require us to remove information about their paycheck 2 weeks ago. How do we know? Right? Well, the best you can do in the face of excision is say, well, information about your pay is not in the system, and I can see that 2 weeks ago somebody removed something from the system. So it's possible that it was in the system and we were obliged to remove it, but I can't tell you more than that. And the thing about it is that in an update in place system, this sucks so hard that you can't even start to talk about it. Right? You can't even start to talk about reasoning about it intelligently. Excision still sucks because the problem is hard, but at least it starts to give you some traction for dealing with the problem. It's also a performance bugbear, right? Because it's the only place in the system where you rewrite indexes like that. So it's not like something that you want to do regularly. But it is, that's there. It's interesting because, people, this always gets brought up. And in fact, the original Datomic didn't have excision. So this was a feature that was added explicitly at customer request. It turns out in reality that in many domains, it was an enabling checkbox feature that people don't actually use. So people said, there's no way on God's green earth I'm going to use Datomic unless it can excise things. And then we said, okay, now it can excise things. And then they use the system and they don't excise. They don't actually use the feature, which we're perfectly happy with because we hate it, right? Because there's a sense in which governments haven't really caught up. Right? How are we supposed to think about these things? We need to be able to talk. Like expunging records, right? If people did horrible things to other people in the United States and it was big in the news and they were motivated by hate or whatever, and we didn't like it, I don't think pretending like it didn't happen is necessarily the right solution. So it's challenging. Excision's challenging. There was another question over here. Yes, Jay.
Yes, are there other key benefits and motivations for you breaking out the new client-server model besides it being familiar to people?
Absolutely. So the question is, what are the motivations for clients? So a big motivation for breaking out clients is microservices. So a big benefit of the peer is the peer library, your application cohabitating with query, can live for a long time and build up a nice warm cache of stuff in memory. It goes back to that performance benefit I talked about earlier of having in-memory query speeds. Well, that's not a great fit if you write lots of little tiny processes that run for 5 seconds and go away. They don't have time to build up a cache. They can't leverage the fact that they have a big JVM. Another benefit of clients is that we have worked very hard. In fact, Rich is going to give a talk at Conj. People are all staying for Conj, right? Rich is going to give a talk at Conj about dealing with dependencies. And that's motivated by some of our war stories here, among other things. And we've worked very hard to reduce the dependency footprint of peers. But the plain fact is that peers do more, right? They have a bigger dependency footprint. They have query in them, and they access storage directly, right? So if you're using a Datomic system that stores things in DynamoDB, then not just your transactor, but also your peer talks to DynamoDB. This is absolutely awesome if that's what you want. But if you're trying to write a tiny process that has a small dependency footprint, then it's not so great. And the AWS dependency itself, they do a pretty good job, but even AWS is a bit of a challenge. We have a problem right now where a customer just called us in the last week and said, I need to be on a more recent version of the AWS Lib that ships with than the one that we currently ship in Datomic, because I'm using a new feature in ECS, and when I have that, I can't get to it with the one that you ship in Datomic. Well, that sounds like it should be easy, right? So, of course, I have to assess if we update this version of the AWS library, then AWS depends on Jackson, which is an XML manipulating library, that some of our storage engines also depend on. Well, Jackson has not been super well behaved about compatibility across versions in its past, which means that in order to decide if I can move the peer library forward for AWS, I have to look at the knock-on consequences for other storages, which are not AWS, right? And that's part and parcel of having a library with a bigger dependency footprint. Clients, tiny dependency footprint, right? They depend on whatever language you're going to use, right? We shipped Clojure yesterday. More languages will follow. So with Clojure, it depends on Clojure, and it depends on core async. So the client, because it is separate, right? That's the other thing, right? Because everything is separate, then it makes sense to imbibe all the recent Kool-Aid about async goodness. And so the whole library is async, right? Everything you do represents things that are happening somewhere else and happens asynchronously. So the Clojure client embraces core.async, which is the Clojure way of doing that stuff. But even that was a dependency footprint thing that we argued about, back and forth, right? Should we make like a callback-based monstrosity and then a little extra client core async layer there? But we decided not to do that. So those are some of the reasons that clients are fit. There's a new page on the doc site, which is probably needs to be about doubled in length, but I've been working on it, that talks about all these differences and other differences in detail that would sort of cause you to choose clients versus peers. One of the interesting things that you're going to notice is that we're going to go through this entire class and all the labs and barely touch any place where this choice matters. Right? We're going to happen to use clients, but we're not going to make any. We're going to go through, all the sort of core capabilities are the same, which makes sense, right? The system is designed to be broken apart into more pieces. So we just did it, right? Yesterday we broke the system apart in another place and teased apart another thing that was together.
And so the peer server was formerly part of the peer app JVM thing. So it's not just the client, but you created the server and the client.
So I would say it the other way around, Jay. The peer server has in it the same code that's in the peer app, but the peer server didn't exist. Right? The peer server is a process entry point. And before the peer server, if you were using peers, the process entry point was your app, right? It's your app. The peer is a library inside your app. All right, let's talk a little bit about getting set up for running the labs. So first off, let me mention, I will be posting these slides in PDF form and putting them online. I've been editing them, you might imagine. Yesterday's release, which I was quite confident was going to happen yesterday, necessitates a ton of change to these slides. So I've been going through and making those changes. So I expect we'll make a few more tweaks. But I will post these slides. You'll have access to them. This page of instructions talks conceptually about what we're going to do, but we're not going to do it this way because you don't have to actually install anything much in the world of clients, right? So we have a spare machine up here at the front. That machine is running the peer server. And so rather than having to run Datomic on each of your machines, you're all going to be able to do your labs just with clients against the peer server. So conceptually what we're going to do is these items on the left, but we're going to do them a different way. So install Datomic. That's going to mean choosing your Maven dependency management tool of choice. So that's Maven or Lining or Boot, whatever you use in the Clojure ecosystem. If you're brand new to Clojure, then Marshall and I and Justin, who's in the back of the room, can help you, make some choices there. Probably Lining is the quickest to get started with. You don't have to install the data sets that we're going to be playing with in the class because they're already installed because we're running the database here in the front. Then you're going to connect to the console. So the console is a wow. So the console is a GUI app that lets you look at data. And so this will let you sort of poke around. So what you'll do is you'll connect and then you'll go up here and you'll choose the MusicBrainz database, which is the full MusicBrainz data set. And then you can try just poking around in here a little bit. And obviously we haven't taught query syntax and everything yet, so you won't be able to do as much. But the UI lets you do things pretty quickly. So I'm going to say find all of the release names in the system. And that was returning 1 million results. So that's pretty quick. Then we will install examples. So there is a repo on GitHub, the Datomic account, that has the examples. Install your own REPL IDE tool. Again, we can make recommendations. How many people already know what they're going to use to hack on with Clojure? So most people. All right. So if you're not sure, then we can help you get something installed. And then play through the CRUD example. Now, it's important that you run Slack while you're in here. So do install Slack because I'm not going to make you try to read connection instructions and all this stuff off the top. Marshall has been and will continue to be dropping instructions for how to get connected to do the labs in Slack. So that's going to include the URL of the machine at the front of the room, the connection configuration for connecting to the database, and so on. And with that, we'll end the first session. Thank you.